everyone. Today we will be discussing about linear momentum conservation and center of mass motion. And these two concepts are very closely connected. That's what the purpose of this video is, to see that connection. And before we start the idea of linear momentum conservation, what it is, we will see that the idea of linear momentum conservation directly follows from Newton's third law. So let's turn our attention to the simulation of Newton's third law and see how Newton's third law leads to the idea of linear momentum conservation. Okay, let's turn our attention to the following simulation and to illustrate the idea of Newton's third law. So as you can see that these two blocks here, they are resting on a frictionless surface. And basically what it means is that if you push one of the block, then other than the collision between these two objects, the force is by the spring, there are no external forces. Of course there is gravity, but that is exactly balanced by the normal force component. So let's start the simulation, and I'll stop it at a moment to show you. Okay, now as you can see here, at this instant of time, say this block was pushing the spring. So say it was pushing the spring with the force which is shown here in this orange color. And Newton's third law simply states that if the block is pushing the spring, then the spring also must push the block with the same force, of course in opposite direction, which is shown here in blue. So these two forces here shown are equal and opposite. And similarly, since the spring is compressed, on the other side this is pushing the block on the left side, and in the same way the block is pushing on the spring towards the right hand side. Now as a net result, what happens is this block, since the force on this block is on the right hand side and the force on this block is on the left hand side, this block starts decelerating and this block starts accelerating. And at the end, since the masses are equal, you will see that the momentum, that is the first block completely stops and the second block starts moving. Let's see what happens. Yes, that's what you can see. Maybe I'll show it to you again, and show the time scale so that we can see it better. As you can see that each instant of time these forces are coming in pair and they are equal and opposite. Now since these forces are basically causing a change in momentum of these objects, and if you see that object 1 starts losing its momentum, and the same amount of momentum, since all these forces are equal in magnitude, so the momentum which this object loses is basically transformed to this object. And as a result, at the end of the simulation, rather end of this when these objects separate, this object stops completely, and this object moves with the velocity v, which this object was possessing. So basically, as you see that Newton's third law basically leads to the idea of momentum conservation here. The same amount of momentum, again you can see, right? Okay, so now hopefully we have understood the momentum conservation law, which is, as you can see, is a direct consequence of Newton's third law. And let's turn our attention to next few simulations. Okay, so now once we have understood the connection between Newton's third law and momentum conservation, let's continue with some more examples. So right now what you can see here is these two masses of they are equal masses. They are resting on this air track. Now we don't need to go into much detail of what an air track is, but basically what happens is there is a thin layer of air which is formed between these blocks and the air track, and these blocks kind of float on this air track. So we can we can just neglect any kind of frictional losses. And let's see, in this case masses are of the same value. Let's start the simulation. Okay, as you see that as we saw in the Newton's third law example, masses are equal, and because of momentum conservation, one mass completely stops while the other moves with the same velocity. Now, in this example, we assume that the collision was elastic. That means that there was no energy loss. These, say, these blocks are made up of perfect steel, and hence, since there was no energy loss, the one object completely stopped and the other object moved. But what if we make the situation completely inelastic? In this situation, this would happen when, suppose, these blocks are made up of, say, mud or something like that, and let's see what happens. Yeah, they completely get they stick together, and then they move. But in any case, whether it is elastic or inelastic collision, the momentum is conserved. Let's see an example where we have unequal masses, because this is a little bit more interesting case. And let's see what happens. Okay, as you saw in this case, none of the blocks have stopped, and they gain different velocities after the collision, but momentum will be conserved. The initial momentum before the collision and the momentum after the collision is conserved. And even if you see the case of if I make the collision inelastic, then these two masses will stick together. Well, interesting thing happens that this time that both the masses were moving in different directions, but after the collision this situation has become something like this. They stick together and they're moving with some constant velocity. They are both joined. These kind of inelastic collisions are also interesting, but the most important point is that momentum is conserved in this case as well. So let's see some more interesting example of a series of bodies, and we'll give initial velocities to this body and this body, and we'll see that something again, I mean, this is an example where, yeah, the momentum is conserved. But interesting point is that here we can calculate momentum before the collisions and calculate the momentum after the collisions, and we can verify that the momentum is conserved. But there is another nice way to see that momentum is conserved using the center of mass motion, and it can be shown, and that will be the next topic of the next video, that if the center of if the momentum is conserved, then center of mass basically moves with a constant velocity. And here I would just give an example. Here we are showing the center of mass, which we will cover in detail in next videos. But before and after the collision, center of mass moves with a constant velocity. Here the velocity, initial velocity was 0, so even after the collisions the velocity remains constant. So our next topic would be how center of mass motion is connected with momentum conservation law, and till then, goodbye.